Good day and welcome to Programming POE Part 3. I'm going to be showing you my application for the Municipal Services application. Right now, I'm just going to run the application. It's going to be a quick video just to demonstrate how the application works and how the service request for POE Part 3 also works as well. So here we have our home page, and we've already done all these pages here. So for Part 1 and Part 2, but I'm just going to be showing you the service request status and just showing you how it works. So basically, we have it here, and initially basically what the service request status is basically users can search through the unique identifiers over here that we have SR001 all the way to 5, and they can also add their requests as well. So they are also sorting it by different categories, by priority, by the date, by their statuses as well. And yeah, so I'm just gonna show you how the application works, and we also using data structures as well. So we are using heaps, we're using graphs, we're using binary search trees, binary trees, AVL trees, and also black red node trees as well, just to receive the request and the statuses as well. So here what we have are different service requests, and over here we can search for one. So, and here we have our related service requests, where related service requests to the request that we do search up is going to pop up here. So if we do search SR001 and we search that up, it's going to pop up here, and we're going to see that the status is in progress. The priority is at number 1. We set it to 1 being the highest priority. Infrastructure for the category, and the created date as well. Here we see the related service request. SR002 is also repairing, and it's also in progress and is pending. So our data structures as well relate to the related service requests that we do have in the application. I'm going to be going you through the code. I'm just explaining how the application actually works. So then if we also search for 003 and we search, and you can see that our related cleanup, garbage collection as well, and it's also being searched through with sanitation as well. So basically how that happens is through the code, and I'll be showing you that as well. So basically this is how we are searching for IDs. We can also sort by priority as well. So priority from 1 to 3, 1 being the highest, 3 being the lowest priority. And we can search through and filter through the list view by priority as well as date, as you can see by how so from the newly created to the oldest created. And then we can also categorize and sort by through status as well. So our status completed, in progress pending. So users can also do that. I also want to draw your attention to here as well. If we just click on it on a specific ID, we can also view the details as well for the ID, the description, status, priority, category, location, and the create date, and as well as the related request for the specific ID, service request ID, and we can do that for numerous for each application as well. So I just want to draw your attention to here. Users can also add a request. So I'm just gonna say water dirty, and here I'm just gonna give sanitation, and priority is high, location I'm gonna say Joburg, and basically I'm just gonna submit, and you can see it's been uploaded here as well into the database. Sorry, not into the database, into our list view, and you can see here we have it here, and it's our high priority as well. We're also gonna add maybe one more, and we're gonna say no, actually yeah, we're gonna say potholes, and we're gonna say infrastructure maintenance, and then we're gonna put the priority to medium, and we're gonna say Joburg as well, and then we're gonna submit, and we're gonna see that it's also been added SR001 into the priority. So now we're gonna sort through by priority. It automatically gets sourced through by priority, but then we can also change the date. Obviously pothole is what we just created now. Then we can also search through and sort by through our status. As you can see, potholes is new, and as well as water dirty is also new as well. And yeah, and we can also see the related there are no related requests for right now. as it's just been added, but everything else also has related requests. And if we search 006, you can see that there are no later requests, but if we search 001, you can see that there are latest requests. So basically, this is just how the service request feature works. If we go back to our main menu, everything has been implemented properly. Now I'm going to go into the code just to show you how it all works. Okay, cool. So now we're in our code, and now I'm just going to show you our service request. So we're in our service request. So this is basically the manager for all our data structures and algorithms. So here basically we're representing a service request with basic properties, and we're also using I comparable as well, just for comparison with our service requests as well. So here we are getting the getters and the setters, and we are getting the ID, description, the created date, status, priority, category, and location as well. And here we are then having a comparison based on priority, like I showed you in the drop down menu. We're implementing or compared to our priority as well. So then here, this is our first implementation into our data structures and algorithms. You can see here we have a genetic tree, generic tree node class for our binary search tree, our AVL, and our red black trees as well. So here we have the nodes data, getting the getters and setters for that, for our tree nodes, for our left right child references. This is for the height for the AVL trees, and as well for our red black tree, we have also sorted our getters and setters. So here we just are initializing a constructor for our new node with data. So basically, gain our data, we also gain our height, which starts at 1, and this is for our AVL balancing, and as well as our is red and black tree. So the new nodes are red by default as well. So then here we get into our main service management class, and we are implementing various data structures. So here I'm going to go through, we are implementing binary search for our tree roots, our AVL tree roots, our red black tree roots, and as well as our minimum heap for priority queue. And we also using dictionaries and adjacent lists for our service relationships, and as well as weighted graphs for minimum search, for our minimum search trees. And yeah, this is basically just a static unique ID as well. So, and here we're also going down, and we also have a constructor that initializes all the data structures. So here we have an object for our heap and our service graph calling the dictionary, and we also initializing our sample graph connections, as well as our operations immediately as soon as the submission is done. Here we are just generating our unique request IDs, and here this is where all our relationships are for the graphs. So we have our added weighted connection graphs for SR001, and like the rest of our rated requests. Here we have a binary search tree operation, and here we just basically inserting a new request into our binary search tree, and then we just using the root and getting the request as well. So, and then here we are making binary search tree insertion. So then here, if node is equals to null, then we are then returning the tree node that has our request. Same here, we are comparing the node data, and we are then inserting into our binary search recursive. Same with here, our node right, we also are inserting our binary search recursive into our right node, and then we then returning the node when the user then searches for an insert. And then here we have our AVL tree operation. So then this inserts a new request into the AVL tree, this method over here, and then we have in our recursive helper as well, that helps with balancing. So if the node is equals to null, then it returns the service request for tree node, and if the request is less than 0, then our node left then rotates to the left, and then the insert also returns node to the right. And then we also update our height and balance. Obviously our height here was 1 if I showed you up here, so that's our starting height for our AVL search tree. And then this then pluses the maximum height that we do get in our search list. And then basically this then updates the balance and the height, and then we then have the left cases and the right cases. This is just again for balance if needed, if there's an unbalanced node data. And then here we have our helper methods for the AVL operations as well. And then coming into our tree rotation methods for balancing. So basically here we just setting the X to the left child of the Y, and then we then saving X's right subtree to T2, and then here we then performing the rotations of X, and then X then becomes the new root for the subtree. And here we are also just updating the heights as well for Y and X, and then we then returning the new root for the subtree as well. And then just to draw your attention on the left rotate as well, is basically the same as the right rotate. We are just assigning the new root for the subtree as well in case of any unbalance. So basically the main purpose for AVL trees is basically balancing the tree by rotating the nodes to ensure that the height differences are minimized. This allows for good and fast operational searches when users are searching up their search IDs with the service requests. So now that we're done with AVL trees, we're gonna go into our red-black tree insertion, and then here we are calling the insertion the recursive insertion method, and we're also ensuring that the root is always black. And here we are just inserting, and this method over here, we are just using a recursive helper for RB tree insertion. So basically we are just inserting the new node if it's null, and we are just inserting the left and the right subtree, as well as just fixing any right leaning red links, or fixing consecutive red links on the left, or just splitting a 4 node into a 2 node. And then this then returns the balanced node. So if there's any unbalanced nodes in our code, then this red-black tree insertion starts working. So then here we just having a helper method for our RB tree operation. So basically the main purpose for a red-black tree property for insertion is so that we don't have 2 consecutive red nodes, and so that the root is always black and always balances the tree with rotations and color flips. And I just want to here, so basically we have color flips. So then if it just checks if the node is red, and it sets the current node to red and sets its children to black. So yeah, that's just the helper methods for the red black tree. So cool. So now that we've done the AVL and we've done the red-black tree, we're going to go into our heaps. So we have our heap operations, and this inserts a new request into the main heap. And this over here adds the request to the heap, and then restores the heap property. And then we have just the maintenance. So this kind of calculates the parent index, and then this stops if heap property is satisfied, and then if it's not, then it just swaps and the current element with its parent, and then it moves up to the parent index as well. So this is again just for faster searching, and the purpose basically for the implementation for a min heap is that it implements a min heap where the smallest element is always at the root. And yeah, that's basically our heap. Then we have our graph operation. So our graph operation, we add in an unweighted edge of the graph. So then here we are basically creating a adjacency list for request IDs over here, and then we are then adding the related requests. So basically the add graph connections are basically the ones responsible for our related requests, and then here we're then retrieving the related requests for given requests. So if we do search SR001, the related request will pop up as well using the request ID and the service graph request that I did show you over here. So obviously those are the weighted connections. Yeah, cool. So and yeah, that's basically our graphs. And then yeah, again, we're just retrieving the related requests, and then and yes, that is just our graph and how we are getting the related requests when users search for a specific ID. And basically the whole purpose for this add graph connection method is just to add and manage graph connections between service requests. And then here we have our BST operations, so our binary search tree operations. So basically we're finding requests using different data structures and then we finding a request in the binary search tree by ID. So when a user then searches, we are then recursively searching for BST we are then searching the binary search tree for the ID once a user has searched for the ID. And then here we are doing the service request. So basically we are then returning null if the node doesn't exist. So this is again a recursive helper. If the node doesn't exist, then, or if it doesn't match, then we then return the matching request. And then here we're just searching the left and the right subtrees. And this basically for the binary search tree is just making it an efficient way to just search a service ID within the binary search tree. So basically this is what these functions are for. And then moving on to our priority request and Trasversal. So yeah, basically here we're just returning all the requests in priority order. So obviously in the drop down menu we have our priority by order, and here we are just storing in a list store sorted requests. So we're storing sorted requests here, and then in a transverse in order for sorted outputs, and then we then return in the result when users do search through for priority as well. And here we are performing in order transversal for the trees. So basically again with the left and the right node trees, we are then visiting the left node tree, and then we are then visiting the root node, and then we visit the right node here, just so that we can have good retrievals for all the requests sorted by priority using in order transversals. So basically this is what this method does. And then here we then having under weighted graph and MST, so minimum search tree. So basically this just adds a weighted edge to the graph, and then we are then creating a adjacency list, and then we adding an edge as well, and then we are then adding a reverse edge for indirect graphs as well. And then we are then using our breadth first search for our graph transversal, and basically this is using our prims algorithm to find the MST. So over here, so here we are using, so basically this is also just queuing and dequeuing the hash sets as well, so that each transversal, so we're using our hash, we're using our queues, and we're using our list, and then we'll be queuing the start ID that the user searches up, and then dequeuing them, and then yeah, getting the neighbor for each visited queue as well. And here the minimum spanning tree, we're just using the prims algorithm to just get the arbitrary start node, and then adding all the initial edges to the queue, and then here we are getting the smallest edge, so we gain the minimum priority queue edge. And then if we then need to skip if already visited, and then we also mark as visited, and then we add the minimum search tree to the weight. And then here we then add in a edge to queue, and then we then return the MST edges. So basically here is just the prims algorithm to just sort out all the weighted graphs and the priority queues, and then yeah, just containing that as well. And then I didn't really know how to show this on our application, so basically what I've done here is I've logged it by creating a new file into our root directory called graph operations log.txt, and then we are writing the messages for the different graph operations. So then we're running the graph operations, and then we logging the binary search tree, the breadth first search transversal results, and then we having a starting node of SR001 because all our requests are always going to start from SR001, and then we are then printing the BFS transversal from this specific node to each node that we have in the file. And then here we are then logging the minimum spanning tree result as well, just to show you the weight from one ID to the next ID. And then yeah, that's basically our whole data structure and algorithm. So we basically talked about binary search trees, AVL trees, red-black trees. We have talked about graphs, graph transversals, minimum search trees, and as well as heaps as well. So we've talked about every essential thing that was required in our POE part 3, and I showed you the code as well. I just want to show you real quick how it works and how it's calling. So basically this is our data that we see in our application, and then here we are then bringing all the data structures that we've used from our service manager, and then here we are bringing the manager class that handles all the service requests and operations and the data structures. Here we are then initializing all the data that I just showed you in the application when it ran, and then yeah, basically all the descriptions, the status, and priority and category. And then here we're inserting each request into all the data structures for comparison. So we're inserting our BST, AVL, RRB, which is our red-black tree, and our heap as well. And then we updating the list view. So here is very crucial. We're inserting each request into all the data structures for comparison, so that all the data structures are able to work together. And then we have our graph relationship. So basically this is what I was showing you for our graph connection in our service manager. So basically I just hard coded these so you can see the relationships as well. And then we're updating the main list view in terms of user searches by ID, or when users search by priority, the description, status, and the ID and everything required we will display. And then we update the list view once the users have searched, and we gain the related service request, and we clear the existing items off the list view. And then we're handling the search by using binary search tree for efficient searching, and then searching for service request by ID and displaying all its related requests. And this is basically the method that handles that as well. And then we find and display the related requests using the graph connections. And we use, again, we're using the binary search tree for searching the request and displaying what we found. So basically, and then then adding new requests is through a separate form that I will be showing you now just quickly. And then this sorts by priority, date, status, and user selection. And then we also gain our prioritized requests from service manager, so that the data structures that handles the priorities are working. And then we update the list view, and yeah, that's basically our service request status form. And here request details form, this is just basically the form for just getting the related services. So here we just gain the related services and operations from service manager, and then here we just initializing everything, and then we displaying all the request descriptions, as well as creating a new list view for the items and adding all the corresponding sub items to our list view. And then here we're just looping through the related IDs using find requests, binary search trees, and gain the related requests from our service manager as well. So yeah, and then we displaying each result that we get. And then this is just for adding the request, which is not really necessary, but it's fine. We do again, we're just ensuring that all the fields are properly created, and then we're creating we gain from service manager all the dependencies injections, and we're inserting in all the new valid requests that user may enter into our binary search tree AVL tree for balancing additional balance with the red black tree and our heap. And yeah, that is basically how we sort everything out. So yeah, this is our whole application. I hope you enjoyed and I loved explaining this, and I hope everything was understandable and I didn't speak fast. So yeah, that is my application for POE part 3. Thanks so much.